this video, we're going to talk about the integration technique known as integration by parts. So in particular, we're going to talk about integrating products, functions that are products, that we can't do from just using a normal, say, U substitution technique. As really the only technique of integration that we know right now is U substitution. So right now, in this particular chapter, we're going to talk about building up our repertoire of integration techniques. So the first one here is going to be doing integration by parts, where we're going to integrate products. So if we're going to talk about integrate products, let's talk about undoing a product rule. So we know the product rule is derivative of the product is derivative of the first times the second plus derivative of the second times the first. So integrate both sides. It introduced the differential notation. We'll just have u times v, no integral sign there because we're going to integrate the derivative, so it's going to go away. Will be the integral of v times du, again, like I said, introducing the differential notation there, and then plus the integral of u dv. So what we're going to think about is this u dv is the piece that we're going to be trying to, this is going to be the integral that we're trying to calculate, and we're going to write it in terms of the other two pieces. So we rearrange this, we get what's referred to as the integration by parts formula. So our integral of u dv is equal to the product of u and v minus the integral of v du. So notice here, as we go from one side to the other, we differentiate the u and we integrate the v. Okay? So there's not any rule that works for every single integration by parts problem. But the way I typically think about them is that I want to try to pick the piece of my product for my u that's going to get simpler when I differentiate it. Okay? And hopefully that becomes a little bit clearer as we do a couple of examples. All right, first one, x e to the x dx. We want to integrate this function. All right, so this is not a form that we know. It's not a basic antiderivative that we know. And it's not a u substitution. Our ordinary thing we would try for u substitution would be let u equal the exponent. That's usually what you use for u if you're doing a u substitution involving e to the x. And that doesn't work here. So we do notice that we have a product for our integrand here, x times e to the x. So again, like I mentioned in the previous slide, I want to, a piece of this is going to be u, a piece of this is going to be dv, and I want u to be the piece that's going to get simpler when I differentiate it. Well, that's not going to be e to the x. E to the x never gets simpler when you differentiate it. It just stays e to the x all the time. So the piece that we're going to use for u here is x. So just to show it kind of symbolically or a little bit more, I don't know, visually, here's my u, here's my dv piece. So usually when you write out your work, you don't write it this way. You typically write it kind of as a table, if you will. U is equal to x, dv is e to the x dx. We differentiate the u. We integrate the v. Okay. All right, so then the integration by parts formula says that this integral u dv has to be equal to the integral, or equal to u times v, no integral. So our u times v here is x e to the x, minus the integral of v du. Now this is definitely an integral that we know how to do. When we anti-differentiate the e to the x here, we just get e to the x. So then the final answer here is x e to the x minus e to the x plus c. Notice back up here, we didn't bother putting the plus c here. We just need an antiderivative here. We will handle all arbitrary constants at the very end, which is what we did here. Let's do another example. Integral of square root of x times log x dx. Again, this is not a basic antiderivative that we know, and it's also not a u substitution. In particular, I really do see a product here, right? I see a square root of x times natural log of x. So if I want to do this antiderivative, I'm probably going to have to use integration by parts. Again, pretty easy to see we have a product, so one of these pieces is probably u and the other piece is probably dv. It's just a matter of picking out which one is which. Now remember again, I said the whole point of this is that, or at least from my perspective, the whole point of this is to pick your u so that when you differentiate it, it gets simpler. Well, one of the simplest things that you can either differentiate or integrate is a power, right? X to a power. Well, notice here if I have log of x, if I differentiate it, I get x to a power. I get x to the negative 1 over x, right? That is simpler. The natural log piece went away. So usually, if you have an integration by parts problem where you see natural log of x, that part's going to be your u. Just as a general rule of thumb, that part will be your u. Just like in the previous part when we mentioned that we're not going to let u be e to the x, that's always going to be your dv, because it doesn't get any simpler when you differentiate it. Same idea. Alright, so u is going to be log x, dv will be x to the 1/2 dx, everything else that's left. Notice here I wrote it as a power, right? Square root of x is x to the 1/2. I wrote it as a power because that's easier to anti-differentiate. Differentiate your u, integrate your v. And again, we don't have to worry about the plus c here because we'll handle that at the end. Integration by parts formula says we take u times v minus the integral of v times du. When we simplify this piece here, we can pull the 2/3 out in front. The exponent simplifies to x to the 1/2. Notice there's no natural log here anymore. It's x to a power, and we just mentioned that that's an easy thing to anti-differentiate. In fact, we just did that here. So when we get our final answer here, we get 2/3 x to the 3/2 log x minus 4/9 x to the 3/2 plus c. Let's do one more example here. We have an integral of x squared sine x dx. Again, we've got a product of two functions here. It's not a u substitution, so good bet it's going to be integration by parts. So again, it's a matter of what to let u equal. Notice that if I let u equal sine x, du would just be cosine x, right? Not really any simpler. It just substituted cosine for sine. And if I differentiate it again, I would get negative sine. All it's going to do is just keep flipping back and forth between cosine and sine with our derivatives. So I probably should let u equal x squared. So I will. U is x squared, dv is sine x dx. Derivative is 2x dx for x squared. Antiderivative for sine x is negative cosine x. Using our integration by parts formula, you get the negative x squared cosine x for your u times v. Remember, the formula is minus the integral of v du. If we pull the minus 2 out in front, it's going to change it to a plus sign. So then we have x cosine x dx here. Notice that we still don't recognize this as a basic antiderivative that we can calculate. However, it did get simpler, right? The power on the x went down. So we can do integration by parts again for this, just this piece here, the x cosine x. Same idea, we'll let u equal x, dv be cosine x. Again, we let u equal x because it gets simpler when we differentiate. Derivative of x is just dx. Antiderivative for cosine is just sine. Okay. Substituting in using our integration by parts formula, u times v minus the integral of v du. I've got parentheses here because in particular this 2 applies to the whole integral, so the 2 would apply to each piece. A thing that some students will get messed up on, which is why I'm definitely putting parentheses here, is if this were still a minus sign out in front, remember it changed to a plus because we had a minus over here. If this were a minus here, it would need to get distributed to both terms. That's a mistake, that's a common error that students will make. Alright, but now we should be able to finish this off. And notice I made the error here. This should be a 2 cosine x right here. I forgot to distribute my 2. So this is minus x squared cosine x plus 2x sine x. And this should be a plus 2 cosine x. Should be a 2 right in front of this cosine, because again, like I said, it should distribute across plus c.